So I'm sorry for the delay. Had some technical problems with the laptop, but now we can start. So first, Happy New Year, and welcome back to the lecture on satisfiability checking. Perhaps some concluding sentences before we start with the new topic. What we did until now, we looked at decision procedures first for proposition logic. That means that you have only Boolean variables. Then we used transformation back to this logic for equalities and uninterpreted functions. And then we looked at the numbers, at arithmetic for the reals and for the integers if we have only addition. That means we had only linear expressions. And what we do now in the next 2 weeks is to look a bit what happens if we add multiplication. That means if we have nonlinear arithmetic. And there we will use this week for short introduction and then look at a method called virtual substitution, which is not complete but very nice algorithmic. And then the week after we will have a not deep but more intuitive short introduction to the cylindrical algebraic decomposition method. So nonlinear arithmetic is more complex also from the decision procedures than linear. That's why we will not go into detail, but we will instead concentrate on the basic ideas of the algorithms. So where we are now, we had two domains, the reals and the integers. After this proposition logic and equality and uninterpreted functions, first we looked at the reals, and there we had the Fourier-Motzkin and the simplex as decision procedure. If you have conjunction of a linear real arithmetic constraint, and we use that in SMT solving to also be able to cover arbitrary Boolean combinations. And then we also had some procedures for the integers. That means if you have linear combination, linear constraints over the terms with where the variables are integer valued, then we had the branch and bound method based on the simplex algorithm. Then we had a kind of more intelligent cut, the Komori cut. And we looked at the omega test, whereas the first two are not complete, the omega test was complete. So the left half is what we already did. And now we come to the right half. If we add to the addition, we allow also additional multiplication, then we have nonlinear constraints. That means we deal with polynomials. And if you have reals with addition and multiplication, that this is the nonlinear real arithmetic, or also called real algebra. And this logic is decidable. This is what we deal with in the next 2 weeks. What we will not deal with is if you have integers with addition and multiplication. And the reason is there are only incomplete decision procedures. This logic is undecidable, so you can encode the whole thing problem therein. So this is the part which we will deal with in the next 2 weeks. So what is new? What we already know, a part of real algebra was linear real algebra. So we had the reals, we had addition, constants, and comparison operators. And now we add the multiplication, which makes it to nonlinear real algebra. This is the first order theory over the reals with addition and multiplication. The syntax is, these are the new parts. Actually, this is the only one. So we have constants, we have variables. These are real values. We have addition, and we have multiplication. Then the constraints are built the same as in linear real algebra. I can compare terms, and formulas are constraints or Boolean combinations as in first order arithmetic. So now I have here only existential quantifiers. Does it mean that I do not allow universal quantification?
No, because we can transform the existential quantifier into universal quantifier by unification.
Exactly. So not exists. Not phi is for all. Phi. So this is the universal quantification can be introduced as syntactic sugar, the same way like disjunction, implication, and so on. The semantics is standard. as you learned it at school. And now there is a bit confusion between real arithmetic and real algebra. I told you that they are both used. So real arithmetic is more used in the SMT, modulo series community. The basic difference is that arithmetic is computing with numbers. So if I write 5 plus 4 is an arithmetic expression, and algebra is the abstraction by using variables and quantifiers and so on. So from this point of view, the real term would be real algebra, but since in the SMT community we're searching for satisfying solutions, so they call it real arithmetic, and that's why they use both, they mean the same. So, and nonlinear real arithmetic, if you look at this SMT competition pages, then this is called NRA. And what we consider is now the satisfiability problem for the quantifier-free fragment of nonlinear real arithmetic. Like in linear real arithmetic, we also did not have any quantifiers. We just had Boolean combinations of constraints, and we wanted to have a satisfying solution for this. Now, obviously, this is equivalent to the problem to checking whether the formulas of the existential fragments are true or not. So if whether there exists variable values satisfying some formulas. So quantifier-free or existential fragments denote the same problem regarding satisfiability. So what is new? What we already know is linear arithmetic. So expressions like given here are real algebraic expression or real algebraic formulas, but also linear real algebraic ones, which we can already solve. What we cannot solve until now are such formulas containing polynomial constraints. Such constraints you know from school, from mathematics, and at school you already learned partly how to solve them. For example, if there are real values, if you would have, for example, you would see this formula here, let's assume without quantifiers, and you should be asked to give a solution for that. How would you try to do this? So what you obviously all do now is trying to find some logical simplifications of this formula or logical solutions without using rules. If I would replace by removing this part, sorry, the other one. Okay, if I would replace these constraints by something like this, instead of this higher order term, I take a quadratic term, then how could you solve that one? That you can solve, definitely. Already at high school. Exactly. So if you have quadratic formulas, then you can compute the so-called zeros of the formula. The zeros, or also called roots, are those values at which the polynomial takes the value 0. So if you have a quadratic, then you can, for single constraints, you can use the PQ formula. For higher order terms, like term 3 and 4, there exist also solution formulas similar to the PQ, but from degree 5 on, there are no such solution formulas. Nevertheless, the logic is decidable, and the virtual substitution that you will get known to this week is restricted to degrees of formulas for which there exist such solution formulas, and the card is more general and complete for all. So, and if we have some higher degree, then for example, we could try to set y0. Then you see that this whole term becomes 0. X squared is always larger than 0. And I can just put x equals 1 and then I have a solution. So I can try to simplify this to get some special cases, but I guess that you did not learn any complete procedure yet for, until now to solve such constraint systems. Before we get to some procedures, some definitions. A canonical form of a polynomial is just a polynomial. A polynomial constraint is just a polynomial compared to 0. Yeah, so the comparison operators can be any. Sorry, this should be a comma. Can be any of those because I can express them also with the negation and the conjunction. And I expect that this P is also in a certain normal form in that it is a sum of monomials. That means the polynomial P is a sum of some terms. Let's start with n. And I have here the variables x1 to x, let's say I have k variables, and they all have some where these coefficients e might be also 0. So, for example, a polynomial in this canonical form would be 2x squared y plus 3xy plus y. It is even ordered according to a certain variable order. If x is before y, then I order these monomials according to the degree of the highest variable. So this is a canonical normal form. We will assume that in most of the time that the polynomials that we consider are in this normal form. And a certain special case is univariate polynomials. That means polynomials in one variable. These are, of course, easier to handle, and to illustrate the procedures, how they work, this is the easiest case for univariate polynomials. And if they have more than one variable, then they are called multivariate. Both of the methods that we will see can handle both uni and multivariate polynomials. So the last one is the degree of a polynomial, and this is just the highest degree of its monomials, that means of these single terms, and the degree of such a term is the sum of the exponents. So, for example, if I have where's the next slide? There are some changes in the menu here. Ich weiß nicht, wie ich eine Folie einfügen kann hier. Das ist nicht im Menü. Vielleicht hier? Ein Stift nehmen? Hier, in Rot. Hatte ich drin. Da irgendwas wurde da aktualisiert. Weg. Okay, that's not so good because I wanted to add some slides, but it must be somewhere over here. Okay. So, for example, if we have this polynomial here at the bottom, then the degree of the last term, a last monomial is 1, y. Then the degree of 3xy, the degree of that is 2, 1 plus 1. And the degree of the so-called leading monomial of the first one is 3. So the degree of the copolynomial would be also 3. And now, nearly everywhere it is called the degree of the polynomial. In some older works you can still read order. Yeah, for example, 2x squared plus 3x plus 1. Only one variable. Exactly. And also already solving univariate polynomials with a degree higher than 4 is not trivial. So this is the remark on the border of decidability. I told you that this logic is decidable. We also use this notation to denote the logic, the reals with addition, multiplication, the constants, and comparison. And the first one who gave the proof that this logic is decidable was Tarski in 1948, so quite some time ago, but not so long as we could expect. And he gave a proof which was constructive. That means he gave a decision procedure, how to decide formulas in this logic. Unfortunately, his decision procedure was non-elementary. That means the time complexity was larger than any finite powers of 2 to the n. So any 2, 2, 2, 2, 2, any one of them is smaller than the worst case complexity. So it is not exponential anymore. It is called non-elementary. So the proof that the logic is decidable was given, but this constructive proof, the decision procedure that he gave, could not be used for practical purposes. So quite a series of other works were done since then. Here's a short historical overview. It starts with two points, Descartes' rule of signs and Sturm's theorem. This was Descartes' rule of signs is a bit older, in the 17th century, and basically what he tried is to count the number of real roots within an interval. And he gave some algorithms how to determine either the number of roots or an upper bound on the number of roots. It is also only for univariate polynomials. And what is more useful is the theorem of Sturm, this theorem allows to compute precisely the number of real roots of a univariate polynomial within a given interval. Now, first to understand the role of these 2 points in what we want to do, if I know, so what is the relation between the roots of polynomials and the satisfaction of formulas of real algebra? So if I would know the real roots of all polynomials involved in a formula, then my statement is that I can check this formula for satisfiability without any problems. Why? Because my formula, and now I would need a new slide. Ja, kannst du mal gucken. Vielleicht übersehe ich irgendwas, ich weiß es nicht. So these formulas of real algebra are basically Boolean combinations of constraints of the form a polynomial compared to 0. That means a polynomial equals 0, or is larger than 0, larger equal, less to equal, or less. So if I know all zeros, the zeros of the polynomials are those values at which the truth value of a polynomial constraint changes. Now, for example, if I have polynomial larger than 0, then this polynomial, assume univariate first. This polynomial, somewhere, let's say its value is positive, it changes, and then at one point it becomes 0, and afterwards it gets negative, then it also has to become 0 before it changes again to positive. So the zeros of the polynomials are those at which the value, the truth value of a polynomial constraint may change. This is the first observation. The second one, how many zeros does a univariate polynomial of degree n have? Anybody knowing? At most n, actually exactly n, but some of them might be complex and some of them may be multiple. So I can have, so to say, I have exactly n zeros, but 2 zeros may fall together, like for the polynomial x squared. If you compute this x1 and x2 according to the PQ, then you will get the same value. That means that the two roots of this polynomial, the two zeros, are the same. So if I count roots, multiple roots multiple times, and I also count the complex roots, then a polynomial, univariate polynomial of degree n has n zeros. That means already finite. Now if I have these first 2 points that I can compute the real zeros, then it also means that by splitting intervals I can isolate real zeros. So kind of I can determine them. So if I know the zeros of a polynomial, then I can partition the state space, since there are only finitely many zeros, I can partition the state space into finitely many intervals in the one-dimensional case, and each interval is such that all values in this interval satisfy my formula or none of them. So I just have to pick one value, and if it is a satisfying solution, then I am happy. If it is not, then I know that none of them. Let's take an example. I have x squared is or let's say any. I have any I have a polynomial of degree 2, never mind which one. And I would like to know if there are satisfying solutions where it is larger than 0. And it does not matter if I know now the... Oh, hast du gefunden? Oh, wo muss ich drücken? Danke. So let us take something more simple, x squared plus 1, larger than 0. I would like to know if this is satisfiable or not. Now let us take, this is x, and this is x squared plus 1. And then it is something like here. So I know it does not have any solutions. What is the reason? I said every polynomial has 2 zeros. Also this one has 2 zeros, but both are complex. So there are no real zeros. And that's why I have one interval. This is the interval from minus infinity till infinity, where the sign of the polynomial is invariant. That means it is always positive. So I have one interval. I just can pick any value from this. If this fits, it's fine. If it doesn't fit, then I know that it is not satisfiable. Now let us take another one. I just take minus 1. Now this polynomial has 2 zeros. So if I take minus 1 and plus 1 as zeros, then what I have to check is the interval basically minus infinity to minus 1, then the point minus 1, then the interval, open, interval from minus 1 to 1, then the point 1, and the interval from open interval from 1 to infinity. Yes, I have one interval here, then this point, one interval here, this point, and one interval here. 1, 2, 3, 4, 5. From each one I pick one value, and since I know that between two zeros the sign of the polynomial is invariant, I try a value here. One value here. Then I have to try this one, the point. I take one here, one here, one here. And if one of the 5 fits, that means if the sign is positive, and which will be the case for this one and this one, then I find a satisfying solution. If none of them fits, I know that there is no satisfying solution for this polynomial. And if I have several polynomials, I take all. So, this is the univariate case. And now I have two problems. First, for that I have to identify the roots. And second, I would also like to handle multivariate polynomials. So I go back to the history. So these two, Sturm's theorem and the earlier Descartes' rule of sign, allow to count real roots within an interval. And how can I use this for determining the zeros? First I use Cauchy bound to determine an interval in which all real zeros are included. This is very simple. This is really amazingly simple how to determine it for univariate polynomials. If I have a polynomial, then I take it in the normal form. I make an example. For example, I have I take the coefficients all of these coefficients divided by the leading coefficient. So in this case, I would take 2 divided by 1 and 5 divided by 1. And I take the maximum value from them. This would be 5. And all real roots of this polynomial lie within the interval minus 5, 5, plus 1, minus 6, 6. So there is a very easy method to determine an interval in which all real zeros of a univariate polynomial are included. Let us make an example, a simple one which we already had with this x squared minus 1. We know how it looks like, approximately. So how many zeros are in the interval? I would like to know an interval in which all zeros are included. So the leading coefficient is 1. And the only other coefficient is 1. So the Cauchy bound tells me that all zeros are within the interval minus 2, 2. And this is true because the zeros are at minus 1 and plus 1. So you see it is over-approximated, but it contains all real zeros. So I have an interval. Somewhere on the reals, I know every root is inside this interval. And I know there are more than 1 zeros. Then I can just split somewhere, count the number of zeros here, count the number of zeros here, and I split as long as In all intervals, there are at most one real root. And then I have now this finite approximation, finite equivalent classes on the reals for this polynomial. So until now, if we can count or determine the real zeros of a polynomial, then we can solve real arithmetic constraints if we have univariate ones. But we have also multivariate ones, and for these, there are two methods, the cut and the virtual substitution, which I do not talk about now because it will come later, and Gröbner basis. We will probably do not talk about Gröbner basis because we do not have enough time, but we will talk only about the other two. So before coming to the virtual substitution, which you should be able to follow after having this short introduction, these methods are also implemented in different systems, like the virtual substitution is in Redlock. It is a certain package of the computer algebra system reduced. Then the cut is implemented in several tools, and there are also several optimizations of it available. Gröbner bases are nearly in every system which is used for computations of with real algebraic terms. And there are also other methods like interval arithmetic. All these systems have in common that they are strong in conjunctions of polynomial constraints. SMT solving, there is actually only one single solver that can now check completely nonlinear real arithmetic. This is an extension of set3, and this is only since last year. So before, all SMT solvers were incomplete, and what set3 implemented is an adaptation of the cut method to this SMT approach, a very elegant adaptation. So this is really actual research, or current research. So what you will get known to, in both cases, virtual substitution and cut, is quantifier elimination procedure. This we already know, as we have for the reals. We also used quantifier elimination before the simplex. And what does it mean? It means that you have a formula, and first we transform it into Prenex normal form. This means that you have first the quantifiers and then a quantifier-free formula. And then what we would like to do is to eliminate these quantifiers inside out, such that we get, after eliminating, an equivalent formula which does not contain the eliminated variable anymore, but is equivalent, or for us it is sufficient to be satisfiability equivalent. So now if we first we remark that if we can eliminate existential quantifiers, then it suffices, because if we have also universal quantifiers, we can express them with existential quantifiers, and since we eliminate inside out, this works fine. So if I eliminate here these two quantifiers, then I get a formula without x7 and x8, then I can negate it, and then I can continue here. So I eliminate also the universally quantified variables by using one procedure for eliminating existential quantifiers. So what does it mean, eliminating existential quantifiers? If you assume that we have a formula here using variable x1 to xn, then if I eliminate xn, then I would like to become a formula here, something like this, a formula which does not contain xn anymore, but it is equivalent. So what is now the problem with this part, which you actually cannot write down this way, because what is strange on this expression? So here what happens is I eliminate xn and I try to use, to try out all values. Yeah, if I try out all values for my last variable x, so xn, then one of them will work, then it is true. Or if none of them works, it is not true. But what is the problem? I cannot try out all values in R because not only that there are infinitely many, but it is even uncountably many. So I even cannot write it down this way, even not with infinite disjunction. But I would like to have something similar, but I would like to have it such that this set is not R, but a finite set. And basic idea is, as I told you, finite zeros partition the state space into finite regions. If you take then the values from each region, you take one value, and then you cover all solutions. So what I would like to have, I have a formula with number of variables. I eliminate one of them by giving an equivalent formula that here I have a disjunction of a finitely many cases. So quantifier elimination for existential quantification is the basic of both methods. Do you have questions to this introduction? Then I would hand over to...
The Cauchy bound theorem holds for multivariate functions of bond?
Only for univariate.
Is there something comparable?
No. No, not that I know. But you can use it by quantifier elimination. Here you have one dimension of polynomials, and it is not quite quantifier elimination. You will see in the card. You can make a kind of quantifier elimination projection where basically the zeros of a multivariate polynomials are projected to a lower dimensional case and then project until you have one dimensional, and then you can use the Cauchy bound and kind of pull up. So you can use the Cauchy bound to get that also for multivariate polynomials, but not directly. You need additional methods. And perhaps one last sentence to the, I told that it is decidable, and I told that the first decision procedure was non-elementary, but I didn't tell anything to the actual complexity. And this is why it takes much longer to get efficient or in practice usable tools and algorithms for this logic, because its worst case complexity is double exponential. But if you have no quantifier alternation, that means only the existential fragment that we deal with, then it is only simply exponential. What is still very challenging, but in practice you can have methods which work in a lot of cases useful or acceptable. So then Florian will introduce you the virtual substitution.
And it's very fast actually. Okay.
I forgot to say, Florian doesn't do
I should know how it works. Okay, the virtual substitution. So you have seen some introduction to it already. Mainly that we want to have some finite set of, let's say, test candidates, which we later will place in this formula for the variable which we want to eliminate, and then we check the remaining formula and go on until we know whether it is satisfiable or not. Okay, so here you see mainly the same as you have seen before in the slide. We want to have this procedure being capable to eliminate one variable after the other, so xn first and so on. And if there's no variable in sight anymore, then you can easily decide whether this formula holds or not, because there are just constraints left, like 0 equals 0 or not 0 and so on. And well, the thing about word substitution, it is, let's say, roughly restricted to degree 2. So it's not allowed, or it cannot solve formulas which have constraints of degree higher than 2 in general. So it's not always the case. It's difficult to make an exact bound, but well, even if you have, let's say, 2 constraints of degree 2, then it's possible that you can't solve this formula. So even this bound is not all right. So the best version, which will always hold, is if there is 1 constraint of degree 2 and the others are linear, then we can solve always with the virtual substitution. So maybe you think it's not much better than simplex, but actually it can solve quite a lot of instances. So many of the real-world instances we have seen until now can be solved by virtual substitution. Okay. And here you can find the basic idea, what a virtual substitution step does. So it takes the original formula and transforms it to a big disjunction about a finite set of test candidates and replaces the variable by this test candidates. And this is the main idea what all this is about. Okay. So let's take a look on how we can construct those test candidates, this finite set. So I will give you some examples. So we have said that this constraint, yes?
So in order to do this, you just have to compute the roots of the polynomial just once, right?
Right.
Okay.
So
for
all constraints. Yeah. Okay. So this is somehow the idea. So if you see this polynomial now here, so a quadratic polynomial, then let's now consider what could happen. So we take one variable fixed, we want to eliminate that variable, and then A and B and C are still parameterized. It does not matter that they could even have, let's say, higher degrees than 2 inside of another variable, yeah? But X does not appear in A, B, or C. So we fix this A, B, and C, but make some assumptions about them. So let's first assume that A is, let's say, 0, and E is also 0. This would be one case, which is possible. Well, what does happen now to this polynomial? How do we call this kind of polynomial? Constant polynomial in X, yeah. Exactly. So this means it would like, for example, if let's say one case is C is greater than 0, yeah, then it would be here. Straight line, yeah. And now if we have a constraint, Gx is compared to 0, yeah, this is the canonical form of a constraint. And let's say we have equal as relation symbol. What do you know then? Does not hold, yeah. So here the solution space of X would be the empty set. Let's say we have greater or not equal. What is the solution space now? R, yeah, exactly. And I just write it in another way. It's the interval from minus infinity to infinity. And that's the same as R. Okay. Let's take another example where, let's say, the relation symbol is now, let's take now a different version. Let's say that B is not 0. Yeah? What's about the polynomial if B is not 0? How do we call this polynomial? A is 0, B is, yeah?
Linear.
It's linear. So if, for example, let's say B is, one case is greater than 0, C doesn't matter actually, then we have something like this. Yeah? Okay. Now, if we have, let's say, equal as relation symbol here, what is the solution space of X?
It's one number, probably minus something.
Yeah, minus something, yeah. What is it, this number? It's here, isn't it? So it is the root of this polynomial. Okay, so it is minus c divided by b, I guess. So let's call this z, 0. Oh. Here we are. So the 0. And I write this down as an interval again. It would be, the point interval from z to z, including z. Yeah, again as an interval. Okay, so if it is, let's say, greater equal, another example, then it would be, the interval containing z from z to infinity. Okay, you see again, we have now intervals, and here is a 0 now in this intervals as a endpoint and infinity. And what is if we have greater? Well, then it's an open interval on the left side. This one here. Okay? And, well, let's say not equal. What is about this one? It's a bit different now. New case. Contains, the solution space is splitted here. So we have two intervals representing the solution space. So from minus infinity to z and from z to infinity. Okay? So for the constraints, we can see that we have always, this solution space can be represented by the intervals, by a finite set of intervals. Okay, let's now take the last case where a is not 0. Now we have to, this is a bit noisy. So if a is not 0, and let's fix that, let's fix that c is greater than 0. Now, what kind of function is it now?
Is the parabola above the x-axis?
Exactly. So let's say it is that one, okay, and z is here, yeah? So then we know, well, if it is equal, then, I have to learn this, sorry. If it is equal, then we know that there is no solution, yeah, for this one, because it's never touching the x-axis. So equal has no solution, empty set. If it is...
This depends on a as well, right? So this only holds if...
Oh, I'm sorry, a greater 0, yeah, of course. Yeah, exactly. So you see it's always on a condition. Well, if it is greater or greater equal, then we know it's r again, yeah? It's always greater, so it's always above the x-axis. So minus infinity to infinity. And if it is, let's say, smaller, then we know again that it is, it has no solution. Okay, so let's take a look on what happens if, let's keep a greater and take c equals 0. So now, it's a bit more interesting. What is happening to the parabola? It is touching, I get this now, touching the x-axis at the point 0. Yeah. That means for relation symbol equal, 0 would be the solution space. Yep.
We assume b equals 0?
We assume, yeah. Okay. So you see, I assume a lot here. So that's quite an important point. It is kind of a case distinction.
Yeah, because you write down restrictions for a and b, but you don't write anything about b, but it's important.
It could be important, right? Yeah. But I think in this case, it's quite clear. If b is what you mean, If it is 0, for example?
If B is 5 and A is relatively small,
Mm-hmm.
it will go below 0. And then you have a second group.
If A is positive, no.
A is 1 and you choose 5.
I don't think so. I think of course, 0 would be a root.
Yeah, 0 would be a root, but you would have an additional root.
Because it's a different way. Yeah, maybe. I'm not sure about this. Yeah, but we will see this later. Okay, yeah. So let's take a look on what happens if C is smaller than 0. Then maybe your case, because I'm making some more cases than I need to make, but I think the general cases which are important include all the special cases. So if it is smaller than 0, it looks like this. So zoom. And now we have, again, roots, which are important. So if it is equal, we have to calculate the roots here. Well, you know maybe from school, PQ or Mitternachtsformel in German, I guess. It is, I think, minus B plus, what is it, 2 B square minus 4AC, root of it divided by 2A. Yeah, and the right one is minus B minus B square minus 4AC divided by 2A. Okay? So this is that 2 and this is that 1. So for equal we have now 2 intervals, one's that 1 and one's that 2. So for let's say greater equal or just greater, then you see it would be from minus infinity, yeah. So this part here, minus infinity to that 1, and this part, that 1 to infinity. So what is missing here now? I mean, kind of an assumption what maybe you have said before would cover this. If you see here, take a look there. What do you know what is not allowed for real numbers? You want just real solutions, not the complex ones. Yeah. Also, but we have here A is greater than 0, so this is already assured. Yeah. Exactly. So another assumption we have to do now is that B square minus 4AC is greater or equal than 0. Okay?
As we have A is greater than 0 and C is smaller than 0, 4 times A times C is always greater than smaller than 0, so if we subtract it, it's always greater.
Yep. A is positive. No, A is negative. No, positive, sorry. C is negative. Right, yeah. But this is just one case. So in general, word substitution does not take so many cases, but it takes cases like A is not 0, you will see later, and C actually does not matter. So I wanted to just point out how this looks like here, how the solution spaces look like. This is an important point we want to take off this graphs here. And if you just remember what we have seen here in the intervals, what are the endpoints always? So you've seen minus infinity being an endpoint and plus infinity, and also the zeros. Yeah. So knowing these endpoints, we actually know how these solution spaces could look like for the constraints. Okay. And this idea we take next. Having a constraint where the degree of x is quadratic at most, we can find, of course, the zeros of this polynomial. That's why it is restricted to the degree 2. And we know, for example, we have this 0 here if A is 0 and B is not 0. And this holds, of course. And for the other two quadratic cases, well, then we have to assume that A is not 0 and that the radicand is not 0, is not negative. Okay. So now we know what the zeros are in general, and then we know how the intervals look like. And here you see all examples which could occur for all these different relation symbols. For example, for p equals 0, we know either it is a point interval or it is empty, could also happen. And if it's not empty, then it could also be completely R. So for example, if the constraint would be p equals 0, like wait, yeah, c equals 0. Yeah. Okay. So here you see the finite endpoints, so the zeros, and the other ones are infinite ones. Good. Now, how can we find out whether two constraints together hold? I mean, for one constraint, we have seen that we can construct the solution space for one constraint. For the other one as well. So if we want to see if two constraints hold, we know the solution space of both. How do you handle those?
Compute them separately and then intersect the solution.
Exactly. So this would be the idea how to do it. You have two solution spaces, you know them as intervals, and you can intersect them. And if you intersect two set of intervals, what do you get again? Set of intervals, yeah. And what the endpoints? You can read or you can think. The endpoints of the intervals of the intersection are endpoints of those we had before. So do not introduce new endpoints in this step, in this intersection step. Yeah. This is a very important fact to go on. So actually, now let's say having our constraints, yeah, and then we make the intersections, the intervals, the solution spaces of each constraint. For every interval, we want to take one value, yeah, inside. And this would be one test candidate. So this is how we construct this finite set. And we take now, let's say, the smallest one inside as a test candidate, as a representative for this interval. So if we have here, let's say one constraint has this solution space, and to infinity, let's say, and then we have another constraint having C2, this solution space, and that's it, yeah. So now you know this is oops. Let's go back. Okay. I hope you get used to this one. So it is this, and now the intersection would be this interval, yeah. And you see the endpoints are the same from those endpoints we had before, yeah. And we say we take for all the intervals we have now here the smallest value. So here it is actually the bound, yeah, the left endpoint, the smallest one in this interval here. Then for this one we take again the bound, And then we have also here the smallest for this interval here. And this is not the bound because it's an open interval, but some value which is very close to it. Yeah. Okay. And we can construct those values because we know the endpoints of all intervals. So you have seen, well, for closed left bounds, we take the bound itself, and for the open ones, we take the value plus some infinitesimal. And we'll later see how this looks like. Okay, so here is a summary of how we act for different relation symbols. For equal and smaller equal and greater equal, we get closed bounds. So we take now the zeros, because we can take this value itself as a left endpoint of the polynomial, which we know how we can construct them, or we take minus infinity. And this means actually a very small value, so just sufficient small. You could also take something like minus some infinitesimal, and then you take, in the end, the minimum of all of them. But this would be more complex to solve it later. So we take just a sufficient small value here. Does not mean, indeed, minus infinity. Okay? So for the other ones, smaller, greater, or not equal, well, here we have open intervals to the left, and then we take a 0 of the polynomial, which we again know how to get, plus an infinitesimal. Yeah. The other case is minus infinity as well. So minus infinity could also always be the smallest value. You don't know, actually. So you don't know how these intervals exactly look like. But if you take all of them, then you are sure. And this is a finite set. Okay, let's take one example here. So construct for this constraint, please, all test candidates. So test candidates are constructed this way. Yeah. So you take a look on the relation symbol. It is smaller. It would be the second case. And then, you know, well, for the first, the zeros plus an infinitesimal. So 0 of this polynomial is I help you. So the 0 would be minus 1 divided by y. But because I divide by y, so this is the second case, the first case, sorry, of the zeros, y must be not equal 0. Okay? And the other case, the other candidate we have is minus infinity, because you always take it. So for one constraint, we get 2 candidates here, which we want to check. And you can see if the constraint would have degree 2 in x, then you would get 2 here and minus infinity. And no, you get here 3, sorry. 3 possibilities, because a could be not 0, then you have 2. That's 1, because a could be 0, yeah? So 3 at all, plus minus infinity are 4. Okay, so the basic idea is now having a constraint, we construct in test candidates, and we do this for all constraints we have. And then we get our set T, if you can remember in the beginning, of a finite set of test candidates we want to check. And if we check all these test candidates and none of them is fulfilling this formula, then we know there is no solution at all. And then it's answered. If there is one, well, then you have the solution, and you will see later how we check those test candidates, because they are a bit tricky. They're not looking like numbers. They have something like plus epsilon, and they are seen here, plus an infinitesimal epsilon, or they have something like minus infinity, and there could be a root inside as well, or a division, which is all not defined in our logic because we have just plus and times. But you will see later how we do check those test candidates. Okay, here's one example left. which I would like to show you. Yeah, that's perfect. How to generate test candidates. So the finite endpoints here are 0 and minus z divided by y. Okay. In this case, of course, y must be different than 0. So we have 3, or actually 2. Then we know the solution intervals are, well, in the first case, if z and y are 0, here and there, well, then we know all this polynomial is 0, and then this constraint always holds. That's the first case. Then we have the case that we have, sorry, the first case of the quadratic case. This gives us these two solution spaces. The second case of the quadratic case is actually the same. And the last one is here for the linear case. Okay. So the set of test candidates is minus infinity, 0, and minus z divided by y. So if you take a look, the left endpoints here are minus infinity, 0, and minus z divided by y. Okay, so indeed these are the left endpoints. It's an over-approximation, of course. Could be that one of these test candidates we find are not left endpoints at all. Okay, so the method, if we take here now an existential quantified formula, you see it has even a Boolean structure inside, so there's an OR and two ANDs. And we want to solve such a formula. Well, then according to our method, now we can find for all the constraints the test candidates for one variable, and we can actually choose which variable we take. So it's not that we have to take the innermost, because we could exchange those two quantifiers. And choosing the right one is quite important in this procedure. It makes a big difference about the efficiency of this method. Okay, so we take, as you can see here, x, and find all test candidates. So for this one, we have no x inside. There's no test candidate. This one as well. Here we have x and there also. And you have seen this one before, so you know about the test candidates from this one. And here it is not that difficult. The 0 of x minus 3 is 3. So this would be a test candidate. And minus infinity is also one of them. If you have more than one constraint, you don't have to take several times minus infinity. Just take it once, of course. So what you get is now a case distinction. See, we have 3 test candidates here, minus infinity, 3, and that one here. And for this one, we have also a so-called side condition. And we have to put them in front of the formula replaced by this test candidate. And which is important to note is that the side condition never contains x. Yeah, so this is very important because we want to get rid of x in this elimination step. And if you take a look here, well, if you apply the substitutions, well, then x does not appear anymore in this partial formulas here, and here does not appear as well. So we have indeed a formula which just contains y. And then we go on with y, and then we get just constraints having no variables inside, and we can decide whether it is satisfiable or not. Yeah. Okay. Some questions left because I want to stop here, and next lecture Thursday I want to show you how to apply the substitution. For this one it's not difficult, but for this one here getting difficult, and for this one as well. Yeah. This is the so-called virtual substitution step. Now over the time. Okay. So are there questions left to here? No?
Why do we intersect the intervals? but then we don't actually care about the intersection, right?
We care about the intersection. We just know that the intersection is, again, a set of intervals, and that the left endpoints are those endpoints we had before. So one of those endpoints of the intervals of the solution spaces we had before, yeah, for the constraints, the single constraints. And knowing this, we can hence construct the left endpoints of this intersection. And we just take all the possibilities as an over approximation of this solution. Yeah. Good. Well, thanks. Ja? Moment, sollte etwas, das nicht.